second day of the workshop. My name is Rogerio Rosenfeld. I'm going to be the chair of today's session. So I just want to announce first a slight change in the program. There's going to be an inversion. So the first talk is by Nicolás Fernández. The second talk, and that's the difference, is James Unwin. And the third talk of the first half of today's session is by Gopolang Mohlabeng. So, this is the slight change in the program. So the talks are 25 minutes plus 5 minutes questions. And the first speaker is Nicolás Fernández. So please, Nicolás, you can start sharing your screen.
Okay.
Perfect.
Okay. So let me know if you can see the cursor, the mouse.
Sorry?
Can you see the mouse?
Yeah, we can see everything.
Okay, so let me thank the organizer for the invitation for this workshop. Has been like very interesting. Yesterday was a really fun day, and today I think I'm the group of the primordial black holes, but I'm gonna talk a little bit about like sub-GeV dark matter and freezing, and this is like a work in progress that we are in preparation with like Jonathan Kahn and Jesse Shelton here in UIUC. And because of that, I welcome comments, suggestions, anything that you think about it. It will be great because yeah, like all comments are welcome. So let me start with some kind of like a dark matter production flow chart, or at least this is how I sometimes I see how is dark matter produced. So you can have different mechanisms, and you can have thermal mechanism or not thermal mechanism. And usually the most, I'm just putting here the most famous one. This is not like a exhaustive list, but it's like some of like the like more famous production mechanism that theoretical physicists has to kind of produce the dark matter. So in the non-thermal camp, we have like the usual misalignment mechanism or inflaton decays. And sometimes I feel like this is a very controversial issue that freezing is thermal or not thermal. Some people say it's thermal, other people say it's not thermal. So I'm just putting the not thermal camp, but freezing has to come from like a thermal dark matter that is the father of the mother, right? But the dark matter is never in thermal equilibrium. And in the thermal side, we can have asymmetric dark matter. So I don't know how much thermal it is because the relic abundance is set up by the asymmetry. But if the dark matter is symmetric, we have the freeze out mechanism. And of course, we have like co-annihilation and all the different ways to produce dark matter. But I'm just putting like these two because I'm gonna kind of like main focus about like the freeze out and freezing mechanism. So usually like people explain what is the freeze out, and it's really hard to have like a new way to present things. So this is my way trying to present this. So the freeze out mechanism, you can think about the art of getting rid of stuff, because usually when like in the, let's say in the WIMP scenario, what happened is that you have dark matter that is in thermal equilibrium with the standard model. And I'm representing this with like, oh, you have a lot of dark matter. And you need to get rid of those dark matter, otherwise you will overclose the universe. So what happened here is that the dark matter is in thermal equilibrium, but then the thermal bath cannot produce the dark matter when the temperature is close to the mass of the dark matter. And then what happens is that dark matter starts to annihilate with itself, filling the Wolfman suppression, and then the annihilations stop because the expansion of the universe. So now the rate of annihilation is less than Hubble. So what happened like now, like dark matter exponentially it's harder to find another dark matter. So what happened in that case is just that the dark matter is just freeze out. Okay, and this is a great mechanism because one is give the correct relic density independent of the initial condition. So here, the dark matter doesn't care about like what was the reheating temperature of the universe, what was the mass of the inflaton. All the initial condition has been erased due to the thermalization. For masses few times MeV, this mechanism is good with like BVN or N-effective, and of course is experimental testable. We have been testing this idea for the past 20 years, and experimentalists have done like an excellent job to kind of like carve out the parameter space of the WIMP. Sadly, we haven't seen any signal yet, but that doesn't take the incredible effort of experimentalists to reach the cross-section needed to test this idea. The other idea is freezing, or the art of getting less but enough. So in this case, unlike the freeze out, you don't have dark matter to that you need to get rid of, because in this case you have that you have like scatterings or decays from the thermal bath that start to kind of like give the dark matter little by little, or how Nicolás said, poquito a poquito. And this also is a really interesting mechanism because the relic abundance is independent of initial condition with like exception. Is also fine with BVN and N-effective for masses or for scales beyond a little bit more than a KAV. And experimentally testable soon, and it's very exciting as we heard that we are having all these new skip experiments, and are soon are gonna reach the important parameter space that is needed for freezing. And to have a reminder, we have a great talk Tien gave yesterday. And so this is a really exciting moment to think about freezing, but also is an important moment to think about like what are the assumptions what we are making, right? And even that people say that the relic abundances set by freezing is independent of initial condition. That's only true if the initial density of dark matter is 0. So in reality, there is like a UV hidden sensitivity, if you think about it, because this assumption of exactly 0 initial dark matter. So this is a point that I want to kind of like test, or I want to push the buttons of how we can test this idea in the freezing paradigm. So what if somehow the inflaton kind of like decay or have some interaction with some hidden sector and the standard model, right? So I'm being very general. I'm not like specifying any inflationary model or any reheating model. Just that this is a very natural way to think that that the inflaton could have a couple, or could have give some hidden sector relic density. And it will be more interesting, right, that if somehow we have a portal between the hidden sector and the standard model, which could change the hidden sector population, or inject some energy from the standard model to the hidden sector sector. So to make this idea more concrete, I'm gonna use the kinetic missing portal. This had been like a really well-studied model, very prolific, if you wish. And this is just, you have the standard model, and also you're gonna have let's say a dark sector with a U1. And the way that the heating sector talks with the standard model is through a kinetic mixing that in this case you can have with the hyper, like with the field of the hypercharge. And in this case, because I'm thinking about freezing, I want the ultralight mediator. And in that case, when you rotate the masses and you cannot select which one is going to be the photon and which one is going to be the dark photon, you're going to have that your Lagrangian is going to be this like in the following form. So to give you an idea of how to read the Lagrange, or what are the important parameters here. So, other important things, I'm gonna think about this mass range. The reason for that is because for masses less than 1 MeV, what is gonna be important is the dark matter coming from plasma decays, and about 1 GeV is the decay of the Z boson to a pair of dark matter also is important, even that our calculation have included the Z decay, but the less than 1 MeV, the plasma decay, I'm not gonna take in account that. So, but it's a safe assumption to disregard the plasma decay up to 1 MeV. So the couplings here are gonna be the epsilon, and which is gonna be kind of like what people sometimes call the millicharge, if you wish, to the, and that's the way that the dark photon talks to the fermions in the standard model. So the fermions acquire like a millicharge to the dark photon, and you also have kind of like a dark alpha dark for the dark photon and the dark matter. So this is the main contribution of the freezing process in the kinetic mixing portal. And this cross section is proportional to epsilon square, which is coming from here, and alpha dark, which is just like the coupling square in the dark sector. So this is why, like, this combination over alpha, if you wish, is what people call the millicharge in reality. But I will leave the parameters in alpha and epsilon because you will see in a moment why is that. So what is my scenario that I'm considering? What is the question that I want to think about it? But, and by the way, the middle term is just the decay of the Z to the dark dark matter. But again, because even that I calculate is in the calculations for this parameter space, it's not a big contribution. So what is the question that I want to answer? So there is some assumption for the freezing case that the initial relic density is 0. So what happens if we kind of like explore something or we start to test that idea? So what I want to explore is like what happens if we have a pre-existing population of dark matter and is thermalized or thermalized in the dark sector, and how that will be affect the freezing. So the interesting thing about the kinetic mixing dark photon portal, if you wish, is that the dominant energy injection is coming only through the dark matter. There is no contribution from the standard model to the dark photons because there is some thermal correction. So because the the photon acquires a thermal mass, in that case, the coupling between the fermions and the dark photon to dark photon becomes epsilon suppressed. So you don't have any injection of the standard model to dark photons, only to dark matter. So that's the only way that the standard model and the dark sector talks. And also, for the moment, I'm gonna assume that the elastic processes are far enough, meaning that I will have a kinetic equilibrium. When the dark matter is injected, it's gonna be kinetic equilibrated in the dark sector right away. So under those assumptions, these are gonna be the Boltzmann equations that I need to solve. So let me explain a little bit more the Boltzmann equation. So this term is just the usual freezing case. So if I'm just solving this for freezing, vanilla freezing, this term will never exist. So this is the term that is in the dark or in the hidden sector. And this is the term that is coming from the annihilation of fermions to dark matter, okay? And the energy that is injected to the dark sector, as explained previously, is only coming from the injected dark matter. And so if I want to know the temperature of the dark, of the hidden sector, I have to solve now the energy density equation. So a couple of points here is that, as you can see, the average cross-section here is respect to the temperature in the of the standard model, but the cross-section of the freeze out or the cross-section of the annihilation of the dark photons, dark matter, is evaluated at the temperature of the hidden sector, okay? And the assumption of instant kinetic equilibration meaning that the dark matter that I injected is right away gonna thermalize. It's gonna have the temperature of the dark sector. So also, I want to test that idea because that instant equilibration. So this is something that I have like the opportunity to ask like the people in the audience that I have this problem of it's just a collision term, but the problem with the collision term is that you have one dark matter in the temperature of the standard model, but the dark matter that you're gonna hit is gonna be in the temperature of the hidden sector. So calculating a collision term of T1 and T2 going to T1 to T2, if you wish, I never seen an equation that it was compact. So, but I discovered this equation. So I don't know if like you haven't seen it before. I will be pretty intrigued and very surprised if you haven't seen it, because I have looked for this and I haven't find it yet. But this is just this is just the momentum transfer, if you wish, between Chi1 and Chi2 when both are in different temperatures. Okay, and this is the way that I'm gonna test the idea of instantaneous kinetic equilibrium. So what is that? Is that the change of momentum has to be bigger than Hubble, and for that, this is the parameter space that is true. So let me just explain this plot. So here you have, again, because all these interactions are only dark matter with dark matter, there is no epsilon, because epsilon is the way that the dark matter talks with the standard model. But in here it's just dark matter scattering with a dark matter that is with a different temperature. And so here you have alpha dark, and in the x-axis you have the mass of the dark matter. The different color lines are going to be for different ratio of the temperature of the standard model, of the temperature of the dark sector over the standard model. So in this case, for example, here, so C of 0.1 meaning that the standard model have 10 times is 10 times more hot than the dark sector. So and the dashed line is just the constraint that is coming from self-interaction of the dark matter coming from clusters, and I just change the ratio of the dark temperature of the dark sector over the temperature of the standard model. So as you can see, there is some parameter space that, for example, here, I don't know if I select a a dark matter of 10 MeV for a ratio of the temperature of 10 to the minus 3. That alpha is almost ruled out, but for 10 to the minus 2 or 10 to the minus 1 or 0.3, it's still like good. And for like heavy dark matter, the parameter space is fine. So of course, like there's different scattering for achieving kinetic equilibrium. So it can be like Baba or Compton. And they pretty much give almost the same answer, a little bit like just maybe like a few percent less for Compton, but you can see that there is a lot of the parameter space that the instantaneous kinetic equilibrium hypothesis is satisfied. So just to recap, everything that is under the color curves is in kinetic, everything that is about the color curve is in kinetic equilibrium. And whatever is about the dashed line is that I will be like in troubles with the self interactions constraints.
Nicolás, you have 5 minutes more or less, okay?
Okay, so now let me ask this to you. So what will be my initial dark matter? So if I plot the ratio of the temperatures over the mass of the dark matter, what I'm plotting here is how much dark matter, like if you're gonna have more dark matter than the one that we measure, or you're gonna have less. So if you have more dark matter than the we measure, so you're gonna need the freeze out mechanism. And if you're gonna have less dark matter than what we observe, you're gonna need to the freeze out mechanism. So this is why I was saying before that the freeze out is the way of get rid of things. So when you're overproduced, you need to get rid of things, but when you're underproduced, you just need a little bit more to reach the dark matter abundance. So kind of like to keep in mind that so in this region, kind of like we need the freeze out mechanism. And for this region, freezing mechanism can happen. It doesn't mean I need the freezing, because maybe I can just also heat up and then freeze out, but I need to be here to be able to freeze in. So if I start to just like crank the code and then find what is the parameter space that I reproduce the dark matter abundance in the alpha dark and epsilon plane, this is what you're gonna find out. So again, the different lines are gonna be like the solid, dashed, and dotted line are gonna be for different ratio of the temperatures. And the red line, everything about the red line, dark matter thermalized with the standard model, which I don't want. So everything that is about that, I don't care about it. And the black dashed line is gonna be just the regular freezing mechanism, assuming that you have zero abundance. So this is the interesting part that you find out, is that, okay, you have like these regions that even that if I change the temperature, you will see that all the curves still are in this like overlap, meaning that they are independent of the initial conditions. So this is like the space where you have leaking and reannihilation, which is something that I don't have time to explain, but they're like expert in the room that know these things. But the interesting part here is that you have this part that change when you change the ratio of the temperatures. So again, the bluish line or blue greenish line, this is for 10 to the 0, which mean 1, which mean the relic abundance. So you can see that here you have a reannihilation, and then you have a dark freeze out, but for different temperatures, you kind of have like this plateau, and then maybe you reach dark freeze out, but for different alpha. Or you can have like this kind of like dip, which is also like a late leaking behavior. And for really, really tiny couplings and low abundance, you reach the freezing mechanism. So there is some UV sensitivity here that you get when you have this population that, or like pre-existing population. What is important about this? So if you look the freezing curve, it's just a line, and this line is just a epsilon square alpha. If you just have the same points but graph I don't know, alpha dark versus epsilon squared alpha dark, you're gonna have a line that is just the same, right? The dark, sorry, the milli charge is just gonna be one value. But here, when now we have this different behavior for different initial condition, you break that 101 correspondent between the alpha dark epsilon and the milli charge. So now instead of having a freezing line in the, for example, in the, when you are looking for dark matter in the electron colliders, and sorry, in the in the, like in Sensei, which is like a electric recoil experiment, now that is not going to be a line anymore. It's going to be a band. So that's kind of like the main conclusion that I want to leave is that that if you assume that there is like this hidden or like pre-existing population, there is some parameter space that this one-to-one corresponding between the milli charge and the parameters epsilon and alpha dark is no longer true, and the freezing line expand to a glaciation band. And by the way, I didn't explain the glaciation meaning, but if you look the picture of my first slide, is because you are freezing in over a existing population, so it's kind of like you are like snowing over snow, which is glaciation. So I think I'm on time, and thank you for your attention, and I'm looking forward for comments or ideas.
Thank you, Nicolás. So we have time for questions. You can raise your hand in the chat, in the participant list, and I can look at. Yes, Jan Tristan.
Yes, should I unmute?
You can ask. Please go ahead.
Yes, yes. Can you hear me, guys?
Yes.
Okay, so
yes.
Yeah, I'm just wondering about slide number 17, because yeah, the Boltzmann equation. Okay. Yeah, the Boltzmann equation here, the second one. Are you considering also the elastic scattering processes for tracking the energy density?
Very good. So yes. So in this case, even that I didn't put the full what I'm really solving, because I'm really also solving for backwards scattering, for example. So, but again, because I'm interested in this regime that I don't thermalize, so those terms are kind of like negligible. So yeah, like I look at them, and the one that are yeah, like I put it then in, even that I didn't put in the plot, but yeah, but in the numerical solution, yeah, I put those terms.
Ah, okay.
Yeah, because you have like some energy transfer between, right, like the kinetic or the terms are here. Yeah.
Okay, so we have I don't see any other questions, and we have time for discussions.
I have a question if we have time.
Okay.
Thanks. It's actually about the very same equation. So Nico, so the capital P is pressure, I guess. So are you solving another Boltzmann equation for the pressure, or how are you treating it?
Okay, that's good. So why I'm doing like what I'm doing instead of solving the raw of the dark matter, where I'm solving the raw of the heating sector, is because I'm summing here I'm summing the dark photons plus the dark matter, right? And doing that, I don't have to, like, the terms that are like the terms that I'm between the relation between the dark photon and the dark matter, they cancel, right? So the only thing that in this term cares about is just what is coming from the standard model, right? And so what is the pressure? The pressure is just
It's radiation then.
No. It's radiation plus the pressure of the dark matter, which is pre-radiation at the beginning, but then becomes zero when the mass and the temperature are comparable. But
Yeah,
but yeah.
This transition, how are you handling it?
Oh no, I think it's Bessel 2 plus Bessel 3 times some factors. So yeah, so like those are known.
Okay, see. Thanks.
Okay, so thank you, Nicolás.
Yeah.
So next speaker is James Unwin. So James, do you want to share your screen?
Hello. Good morning.
Good morning.
Yes.
So maybe Nicolás can unshare. Yeah. Okay.
Let me do that right now.
Yep.
Start video and share screen. Okay.
Yep.
Can you see that?
Yep. So I have 25 minutes and 5 minutes of questions. Thank you, James.
Okay. Okay. So thank you very much for this invitation to speak. I want to talk about a somewhat provocative topic. I want to ask, could there potentially be a black hole at the edge of our solar system? Now, your initial answer should be, that sounds absurd. But what I hope to do in this talk is make a few interesting observations which have been made in the astrophysics literature, and give them a little twist that makes this question become not an immediate no, but something a lot slightly more thought-provoking. So before I start, I'll just point out that this is work with Jacob Schultz, and you can find a link to our archive here, and this work was published in PRL. So the rough breakdown of the talk, I'm going to go a bit quick because it's a short talk, but I'm going to sketch the idea that there could be a ninth planet in our solar system, in particular a large, sometimes called super Earth sized planet in our solar system. Then I'm going to argue that maybe it's not a planet. In particular, I would like to suggest that it could actually be a black hole, as the title of this talk. And then finally, in the last part, I'm going to ask, how can we look for this? And one particular way to look for this is to look for its dark matter annihilation signals around this object. So it's quite interesting that if you just take our sort of standard knowledge of solar system formation and Newtonian physics, then the structure of the solar system is well known and well predicted and explained out to about 100 astronomical units. For reference, the Earth sits at about 1 astronomical unit, Pluto sits at about 50. And so we pretty much have a good explanation of the solar system over most of the sort of region of interest. Now, what's more interesting is that if you go out to further distances, well beyond Pluto, out to say 100 AU and beyond, then our explanations start to suffer. In particular, there are populations of planets, also or planetesimals they're called. These are sort of small objects at say 250 AU and beyond, whose orbits we actually are struggling to understand. These things are called trans-Neptunian objects because they lie past Pluto. You can think about them as being objects from the Kuiper belt, and they have some features which are difficult to explain with the theory as we know it. These are, for instance, there are unexplained clusterings of these objects. So you would think that these objects which exist should be sort of uniformly distributed on the sky. What you find is that they actually cluster into certain regimes. So you find a dozen, say, all in one direction. This is actually supposed to be indicative from the plot in the top right here. There are also some odd things. So you have to think about these. This called Keplerian coordinate system. It's just a way of measuring objects in a reference frame of the solar system. But there are these objects called the high perihelion objects. So-called the Sedna is one given planet, and collectively these things are called sednoids. And explaining why these things have these odd orbits, which were so-called high perihelia, is another question. And finally, another point of these transit-tuning objects which aren't understood is some of these, all the planets, of course, lie in a plane, and there are some things which are extremely high inclinations, and these objects are going almost perpendicular to the plane in their orbits. And again, understanding these sets of objects cannot be explained within the sort of standard theory. So all of this information was sort of very nicely brought together in this paper of Battigan, Adins, Brown, and Becker, this physics report. So if you're interested in these anomalies, then I will direct you there. But to get to the sort of bottom line, the idea is that you can't explain the positions and existence of these objects, in particular the random and this alignment of these trans-Neptunian objects through chance or through observational bias. In particular, for the idea of this clustering of these objects in one part of the sky, that it was estimated the chance of this being random alignment was 1 part in 15,000, which it could happen, but it's highly rare. On the other hand, if you were to add in just one extra large body at the edge of the solar system, then you would find that you could actually simultaneously explain all of these anomalies in these planetesimals past Neptune. However, the body you have to add in is kind of strange. It's a relatively large planet, say 5 to 10 times the Earth's mass. It has a highly inclined orbit, quite elliptical, and in particular, extremely far away. So you can see that these sort of benchmark models pitch this planet 9 at being 450 to 700 AU away from the Earth. So that's roughly 9 times, away from the sun. That's roughly 9 times further than Pluto. So this is an odd place to find a planet. So how would a planet get there? Well, there are basically 3 theories. The first is perhaps it formed there. It simply formed like a normal planet would form. The second idea is that maybe it formed in the inner planet forming region, maybe near the giant planets, and then was kicked out by some particular dynamics of the sort of overcrowding in the early solar system. The problem with this is once it's kicked out, to circularize the orbit, you have to then add in an extra third body. So you need to basically have a passing star very opportunistically rescatter this planet back into a stable orbit. And the third idea is that perhaps this was formed in a different solar system. In the early universe, it was kicked out of that solar system and then later captured by our solar system by some fortunate circumstance. So let me just highlight that the idea that this is actually just formed in the outer solar system, I think, is the most far-fetched, formed in place, because there's simply not enough material out at 700 astronomical units to form such a large planet. There's also not really enough time for essentially for it to accrete. So this basically gives 2 possibilities: the bouncing out, which again it seems extremely difficult, or the gravitational capture of a extra solar system planet. And I actually think that the capture is by far the most likely scenario. Now, what's interesting is if you're capturing a planet, you could immediately ask, why does it need to be a planet? All I can ever see of this thing is that it has some sort of strong gravitational attraction, which influences the bodies in the outer solar system, therefore changing the orbits of these trans-Neptunian planetesimals. So being a particle physicist, the first thing I want to do is I want to consider some of the more unusual possibilities. Perhaps this is not a planet. Perhaps this is an exotic star of dark matter, or perhaps this is a very small, compact dark matter microhalo. Or in particular, perhaps this is a primordial black hole. Now, the idea would be there is a population of primordial black holes in the early universe that makes some fraction of the dark matter energy density. And one of these just happens to get caught in the gravitational field of the solar system and bound to a stable orbit by some fortunate circumstance. So what is a primordial black hole? A primordial black hole is similar to an astrophysical black hole, but different in both its origins and its characteristics in the sense of its mass. These primordial black holes are normally formed by essentially overdensities in the early universe. And because these aren't formed by stellar collapse, it means they can have an extremely large mass range. And depending on your model of cosmology, you might predict these things lie at some different mass. So it's not entirely unbounded, as is well known, that these things, if they're too light, they'll evaporate through Hawking radiation. And you can also place various experimental bounds. So I pulled this nice plot from a paper of Carr and collaborators. What you can see is that this is the mass of a primordial black hole over the mass of the sun on some log scale. And you can see if I make this a small fraction of the dark matter density, this FPBH on the y-axis, then I can take an extremely large range of masses. Okay, very good. So you could do this, right? So I want this to be an Earth mass. That's about 10 to the minus 6 of the sun. And you can simply ask yourself, what fraction of the dark matter relative density would I need this to be a viable candidate to be planet 9? And initially you feel like you have a lot of freedom, but there's an interesting second link you can then draw, which is to this recent observations of the so-called OGLE telescope. So it just so happens that the OGLE telescope has been looking for populations of primordial black holes, and they came up with a reanalysis of their data came up with a tentative excess indicative of a population of primordial black holes with a mass between about 0.5 Earth masses to 20 Earth masses and occupying a fraction of the dark matter relative density of about 1% to 10%. So you can see that in this plot here on the right-hand side, specifically this blue region. Now, remarkably, this is exactly the right mass range to account for these gravitational anomalies in the outer solar system if one such primordial black hole got gravitationally captured. Recall that what we wanted was an object of about 5 to 10 Earth masses. So there's a very neat overlap between these two experimental hints. So let's roll with this and let's take this as a given now that this primordial black hole population has some support. And what we can ask is, well, the first thing to note is it's not all of the dark matter, clearly, but it makes some reasonable fraction, maybe 1%. And we can ask, if these things are around and they count for 1% of the dark matter, that means we know their abundance. What is the chance that we capture such an object versus capturing a planet? Of course, if primordial black holes exist and planets exist at the same time in our thinking, but still the capture rate for planets is much higher, then we should just ignore this prospect of primordial black holes because it would be disfavored by Occam's razor. But we can actually go ahead and calculate the capture rates, or at least estimate the capture rates, and we find something very interesting. So I'm going to go through this slide very quickly, but I give references. And basically, the capture rate has some given form, and if you go ahead and you plug in all of the various numbers that correspond to a population of rogue planets, which are estimated in literature, and it corresponds to a primordial black hole, which has a similar velocity distribution to the dark matter halo, and an abundance given by this OGLE excess. If you actually go ahead and do this calculation, what you find is that these two values, the capture rate of black holes and the capture rate of free floating planets or rogue planets, turn out to be comparable. So you can see here, this is on the bottom line. This goes essentially like an order 1 factor times our best known values for the various number densities, velocity dispersions of these objects. So that's very interesting. It tells you that you can't immediately discard this prospect of capturing a black hole versus capturing a planet, assuming this OGLE excess. So say that such a primordial black hole existed. The next question you might like to ask is, how do you look for it? Well, recall that I said that this is not all of the dark matter. It's some fraction of the dark matter, perhaps 1%. What happens to the rest of what composes the rest of the dark matter that we need to account for observation? Well, it's naturalist to assume that the rest of the dark matter is just some normal particle dark matter, be it a WIMP or be it some other, whatever your favorite dark matter candidate is. And I'll tell you what my favorite dark matter candidate is in this scenario in a second. Now, what's interesting is once you have this primordial black hole in this sea of dark matter, it will start to actually accrete dark matter after it becomes non-relativistic. And it will actually form an extremely dense halo around these primordial black holes. So every primordial black hole has a highly dense halo of particle dark matter, sometimes called a dark matter spike, specifically because it's just so extremely dense. And again, I will talk about this only briefly, but the interesting thing to extract from this is that you can actually calculate this dark matter profile. The actual precise details are a little bit intricate, but the bottom line is that it has a very characteristic profile, which is thought to go like this 9/4 power law. And it's specifically this 9/4 power law that makes it so strong in the annihilation signal. You could actually worry that the inner region of the dark matter halo might annihilate away. But what we calculated in our paper is that for this particular mass range, that doesn't happen for the sort of cross sections which aren't immediately excluded. That is the annihilation cross sections of the dark matter, which aren't immediately excluded by experiments. So there's no inner plateau that you might get from annihilating away in the particular scenarios we'll be interested in. So that's very good. So now I know what my density profile is, and I realize I haven't given many details on the derivation here, but you can check the references and you can check our paper for the specifics. One other thing you might like to note is that this power law does not have an indefinite extent, but if this primordial black hole with its encompassing halo, it's captured in our solar system, it will have a terminal radius to it, which is set essentially by the point where the dark matter is stripped away by other gravitational sources. In particular here, you get a tidal stripping from the sun, which will cause the black hole, the halo around the black hole to slowly be stripped away by this tidal gravitational force. And the final terminal radius of the halo is set by the so-called Roche limit. And this is a very simple calculation. And you can show that if you think that your object lies about 400 AU, 500 AU from the sun, and it has a mass of, say, 5 Earth masses, then it tells you that the total extent of the halo around this object is about 8 AU. And any dark matter beyond that would simply be taken away by the sun's force and redistributed. So that's kind of interesting. 8 AU is roughly 10 to the 9 kilometers, and so you can compare this to the mass, to the radius of the Earth mass black hole, which is about 10 centimeters. So you have this very interesting hierarchy of scales. In fact, you can think about this as that you have a 10 centimeter primordial black hole, followed by a 10 to the 9 kilometer halo, and then of course you are almost 1,000 AU away from the sun.
James, you have around 5 minutes, okay?
That's perfect. Thank you. So very good. So now I have this dark matter halo around a primordial black hole at the edge of the solar system. The next question is, how do you look for this thing? Well, the classic way of looking for dark matter is to look for indirect detection signals. This assumes necessarily that the dark matter annihilates. So let's take one particular example. Let's assume that the dark matter is a WIMP. So it has a characteristic cross-section of 3 × 10⁻26 centimeters cubed per second. And we can then pull this out. I think I forgot to put a reference here, but I think this is to the paper of Adamek that I had a few slides back. And I can ask, I take an Earth mass primordial black hole, which is about 10⁻6 solar masses. So in this sort of vertical orange band, which I added to this plot, and you can look at the limits. Well, the limits tell you that you're extremely excluded if you want to have 1% dark matter, which is shown in the horizontal orange band. So this red line, I think, is essentially a Fermi limit on this. And it says that if you have 100 GeV dark matter, then you're extremely excluded. If you have 1 TeV dark matter, then you are marginally excluded. So perhaps if I make my dark matter right at the edge of the unitarity bound, or I play some tricks, maybe this model passes. But it's not clearly not WIMP. WIMPs might not be the best way of approaching this. So let's take a different type of dark matter just to prove that this is a reasonable setting. And if not WIMPs, my second favorite scenario is so-called freezing dark matter, where I start with a negligible amount of dark matter and I slowly generate the relic abundance by production. In such models, the production cross-section is set by, or at least in one class of models, it's set by the dark matter coupled to the standard model thermal bath via some mediator phi with mass m phi, and couplings g to the dark matter and lambda to the bath. Lambda, you should think about it being very small, and g can be on order 1 coupling, and then the relic density will actually scale like lambda squared. And parametrically, you can write down something which matches the relic density for, say, a mediator of 10 TeV, an extremely small coupling, say 10⁻12, and a dark matter mass of 100 GeV. This thing kicks out a characteristic annihilation cross-section, which is extremely small, maybe 20 orders of magnitude smaller than the sort of WIMP scenario. So this is 10⁻56 centimeters cubed per second. So let's now take this so we can ask, can you see this? Or can you avoid, also can you avoid detection? So given this annihilation cross-section, you can calculate the annihilation rate of a body which sits 100 or 400 AU away from the Earth with some characteristic profile and this annihilation cross-section. And when you put this together, you find some particular rate of annihilations. So here I've got my cross-section as a function of this characteristic rate. So if I vary the cross-section, this will enter as some multiplicative factor. Similarly, varying the dark matter mass will also change this result. Now, once I have this, I'd like to compare this to something, and the natural thing to compare it to is, say, some sort of indirect detection, maybe some point source object in the Fermi catalog. So given the rate, I can now calculate the photon flux coming from a source which is 500 AU away. So I'm going to take R9 to be the radius of planet 9, 500 AU. I'm going to assume, just as a sort of very blunt assumption, that each annihilation produces about 10 photons through a cascade. And I'm going to put all this together to extract some sort of flux. And I'm going to compare this to the smallest detectable flux in the Fermi catalog. This is roughly 10 to the minus 11 photons per centimeter squared per second. And if I take this smallest, this dimmest source that Fermi says it can see, and I use the Fermi flux above, I use the photon flux above, it gives me a limit on the annihilation rate, which in turn gives me a limit on the annihilation cross-section. And you can see the limit comes in at about 5 × 10 to the minus 56 centimeters cubed per second for this given dark matter mass, which just happens to lie close to the characteristic annihilation cross-section that I previously sketched for this freezing model this characteristic freezing model. So it tells you that freezing dark matter gives you a scenario where you generate a dark matter relic abundance, which then can accrete around a primordial black hole, which doesn't give annihilation signals that exclude such a model, but actually lies on the cusp of exclusion. So you might hope that the next generation could actually test this scenario and experimentally confirm it. So this brings me to my conclusions. So let me just first say that the tentative evidence for these trans-Newtonian objects pointing towards a new massive object in our solar system is extremely exciting and interesting, be it a planet or be it a more exotic object such as a primordial black hole. Should it be a primordial black hole, that would be, of course, a revolutionary discovery, which has the opportunity to tell us much more about cosmology, solar system formation, and of course, fundamental physics. The next thing I'll highlight is that these OGLE events, these unexpected microlensing events seen at OGLE, are also independently extremely interesting. And I would say that these are still tentative, but if these panned out, then this would be something that could be of great interest to the community. It is quite remarkable that these two excesses hint at the same mass range, and this is what really drew us to write this paper and start thinking about this seriously. In particular, once we realized that the capture cross-section in this scenario was similar for both planets and black holes. But really, one of the most interesting things about this is that if you take this seriously and you think that there's an object in the outer solar system, and you don't restrict yourself to think about planets, that tells you that the way you would search for this could be very different. So of course, if you're searching for this as a planet, you're looking essentially for visible light, which is reflected. And people have done these searches and actually excluded a whole range of parameter space. But if you now start thinking about this as a different scenario, as a primordial black hole, which perhaps leads to indirect detection signals, then you can start searching for this in gamma rays or some with other more broader or tools. And this has already generated some interesting research in this direction. So I'll just highlight a few of these before closing. So Witten proposed building a fleet of micro spaceships to go and search for this, sort of grand mass spaceships to flood, and hundreds of these to flood the solar system and search for gravitational signals of this primordial black hole. Suraj and Lowe proposed using LSST to actually try and pinpoint this thing. And more recently, Henges had proposed using the dark energy survey to look for this primordial black hole. So already, and actually there's a few other ones. These are just my top picks right now. So I think this is a very exciting possibility, even if it is highly speculative. You know, sometimes you need to, you know, high risk, look for high risk, high reward scenarios. So thank you very much for your attention. I hope you found this interesting.
Thank you very much, James, for this very interesting talk. And we have time for questions. So Diego, please open your mic and ask.
Thank you for the talk. How anisotropic is the signal expected for direct detection experiments?
I mean,
extremely.
Yeah, because I mean, so this is a point object which is very close, so it would come from a specific point on the, you know, a very localized point on the sky. However, there's actually a very important point, is that as well as getting, and this is a point we raised in the paper, but I skipped in the talk, as well as getting signals from the object in which is captured by our solar system, there's also a population of these objects, these primordial black holes throughout the galaxy, and in fact extragalactic. And so as well as having this nearby point source, you would also have an isotropic flux coming from the greater population of these objects. It just so happens that the nearby object, because it's so close, tends to give the leading bounds. Does that answer your question?
Yes, thank you.
Okay, more questions for James?
I have a question.
Yeah.
James, thanks for the talk. So about the OGLE excess, So this it's a telescope, right? It's not pointing towards
Yes.
the planet 9, right? Or
No. It's in fact it would be incredibly difficult to pinpoint where planet 9 is to point towards it. That's actually one of the mysteries. You don't know. You just know that its rough orbit, but often the way they calculate this is by averaging over its orbit to calculate its effect. So we don't know where it lies, and in fact the range of orbits takes a huge amount of sky. So OGLE is actually looking at the galaxy as a whole, or at least a large part of it.
okay.
And they're looking for microlensing. Is that correct? They're looking for microlensing, James?
Yeah, so it's not, exactly. So it's not microlensing of this Planet 9 object. It's microlensing of primordial black holes in general throughout the galaxy. So you're looking for a primordial black hole passing by a star, not nearby a star, not in our foreground, but in the distance. Does that clarify?
Right, and that's how many of these bounds that you showed are actually found, right, by this microlensing. Yeah, but also this paper of Carr, the plot from Carr is probably microlensing. Many of these are microlensing.
Many of these are microlensings, quite. And I also say this is the monochromatic limit, so it assumes that they all have the same mass. So you can of course play with these bounds, but this actually gives you a good characteristic. Maybe Stefano will say something. Is Stefano talking? Maybe Stefano will say something on.
Okay. And also, did you assume for the photon spectrum? Did you assume anything, or would it help to get some information on the photon spectrum?
Yeah, no. I mean, so we did the most bluntest thing you could possibly do in doing this, which is essentially we just assumed that you got 10 photons per annihilation. Really, what you want to do is you want to write down an explicit model where you dictate the exact couplings, and then you run this through Pythia or some similar program to extract the photons that come out in each annihilation. It's something we're working on. But the thing is that this, if you just make simple assumptions like this, it gives you reasonable order of magnitude bounds.
Okay, so let's get one last question from Nicolás Fernández.
Hello, James. Can you hear me?
Hi. Yes.
I'd like to know the existence of this object would have some considerable and measurable consequence on gravitational fields of our inner planets.
Yeah, so it's extremely far away, and so I think it's unlikely. I think it's unlikely. It's so far away, even though it's large. You really just see it changing these orbits in the outer solar system. It's a reasonable question, though, about what is the extent. In fact, let's put this another way. I think you can actually use things like the orbits of certain planetesimals to actually constrain this. So if you think you know the orbits well of, say, Pluto or Neptune, then these will actually tell you some constraints on where you think this thing can lie. And in fact, the way they do this the way they do this a lot is through simulations. So they simulate orbits and they ask, would this lead to a disruption of sort of known orbits? Or can I reproduce the known orbits of the solar system, including this object without messing anything up? And by running these simulations over and over and over, they get some handle on the possible orbital paths of this. Again, let me just go back to my starter slide, or actually it's not on my starter slide. Let me go back to this slide and plug this paper by Batigan, Adams, Brown, and Becker. It's 100 pages or so. It's extremely interesting, extremely insightful. It would make excellent weekend reading to anyone who's interested.
Great. Thank you again, James. Sorry.
Thank you.
Sorry.
Go ahead.
I imagine other trans-Neptunian objects could be used for finding these objects beyond the...
Well, yeah. Quite. So, I mean, this is one of the questions of... This is one of the questions of... One of the questions of observational bias. which is perhaps the reason why we see the clustering, for instance, is because we can't see all these objects. And I think it's certainly true that we don't see currently or have a good or good knowledge of all of the objects at the outer solar system. And that we are continuously getting more information and more data about where these objects are, what their orbits are. It's quite plausible that once we have better information that some of these anomalies might go away, or they may get substantially stronger. So yes, so more information about the orbits of these things will come in the next, say, 5 to 10 years. And this will give us a better picture of both whether there's something out there and if there is, where it is. And I think it's very exciting to keep a watch on.
Yes.
Okay, thank you very much,
Thank you.
James, for your talk. And let's move on. So next speaker is Gopolang Mohlabeng. So maybe James can stop sharing his screen and Gopolang can start sharing his screen.
I'm trying to, but I think my computer has crashed.
Okay, I'll do that for you.
Can you stop it? Thank you.
Yeah. So Gopolang, can you share your screen, please?
Yeah. Can you see my screen?
Yeah.
Can you see my slides?
Yes. Just put it full screen or presentation mode. Yes. Thank you very much, Gopolang.
Okay,
so go ahead. Go ahead.
Okay. I first want to thank the organizers for inviting me. Because actually, this would have been my first time going to Brazil, so it's too bad, like everyone else, that we can't actually be there in person. But so today I'm going to be telling you about prospects for ultra-heavy dark matter phenomenology. Before I start my talk, I usually like to introduce myself. So I'm from South Africa, and in my native language, my name is pronounced Gopolang with a ch, and it means remember. But usually people can't remember it or they can't pronounce the ch, so I just ask people to call me Gopi. So this is work that has been done with Human WSL at Brookhaven, and it's based on these two papers. So the outline for this talk, I'm going to give a very, very quick overview of current searches for dark matter. I'll talk about a model for ultra-heavy dark matter that is motivated by possible new striking signatures in direct detection experiments. And then I'm going to discuss how we could possibly get or produce these kind of particles in the early universe. So we are all dark matter enthusiasts here, and there's no reason for me to try to convince you that dark matter exists. We all know that it exists. We've seen enough gravitational evidence of it that tells us that we have it from the smaller scales to the larger scales in our universe. However, we have no idea what it is. If it's a new particle, we don't know what kind of mass it has. Does it have any spin? Does it decay? Is it a stable particle? Besides gravity, we don't really know whether it even has any interactions with us. Is it an elementary particle or is it bound state? We have no idea about this. And I would argue that to have any hope of actually probing it, we need to look for its non-gravitational interactions with us. So, a lot of people could argue that if we have primordial black holes, then gravity can actually tell us a lot about this as well. So this is actually new exciting work that is being done, as we saw from the previous talk by James. And so the range of possibilities of what dark matter could be is huge, right? So we have dark matter could be anything from wave-like at like 10 to the minus 22 EV, all the way to the Planck scale, or even beyond, in the form of primordial black holes. We just heard about in the previous talk, and we're going to hear a lot about primordial black holes in the coming talks later today. So since this range of possibilities is so vast, we have to start somewhere. So, our history of particle physics is that we had these other theoretical problems that we were dealing with, and we found ways beyond the standard model to solve this. And lo and behold, by trying to solve those problems, like the gauge hierarchy problem that led to supersymmetry, this actually gave us motivation for studying WIMPs. So and leading us to the WIMP miracle. So this gave us a starting point of where to search for all this dark matter. And so recent searches, rightly so, have been focused on searches in the WIMP region of parameter space. We have direct detection, where we have a large range of experiments that have searched for dark matter interacting inside and underground experiments. We have indirect detection and collider searches for these particles. Unfortunately, this is very heavily constrained, as we haven't seen a convincing striking signal of dark matter. Now, this has motivated search away from the WIMP scale, or a few rather beyond the WIMP region, mainly towards low masses, where we have a large range of exciting new experiments or experimental ideas to search for both particle and wave-like dark matter. So for the direct detection case, we have new materials that look for that can search for low mass dark matter in the form of bonons, magnons, and we've heard about some of them yesterday from Tim. This actually coincides also with the type of mechanisms that people have come up with that can actually reconcile with these kind of low mass dark matter experiments. And the tabletop experiments that people are coming up with as well to search for other lower mass targets. And there are many other great ideas that people have been looking at. So the question that we could ask as well is, can dark matter be heavier than WIMPs? Well, of course it can. How heavy is heavy? Well, why don't we be ambitious and look at the larger scales in our elementary theories, like the Planck mass scale or the scale of quantum gravity or the gut scale? These are reasonable targets that we can possibly achieve. Look at. And so hereby, when I talk about ultra heavy dark matter, I mean any dark matter that is larger, any particle that is larger than 10 to the 5 GeV mass. So how do we find this dark matter? Well, let's try to go through the detection methods that we already have and love. With indirect detection, we know that the flux of annihilating particles, especially in our region, it goes as 1 over the mass squared. So if I have a 10 to the 16 GeV particle, the flux is negligible, so I will not see those particles, the flux of those particles. However, if, say, I allow the dark matter to decay at late times, in principle, I could have dark matter accumulating in the center of the galaxy and then decay at late times into, say, ultra high energy cosmic rays or ultra high energy neutrinos. And we have a very good detector for this by the name of IceCube that could look for these types of signatures. And a lot of people have actually looked at these. I forgot to put some references in, so I apologize for that. Colliders, we have no hope of finding such heavy particles at colliders, so this cannot work. Direct detection, on the other hand, is another avenue that this could be possible. So the number density, instead of going as 1 over the mass squared, it goes as just 1 over the mass. And so even though I have a smaller number density of a small flux of these particles coming in, maybe I could use this as leverage. Let's explore this a little bit more. If we look at the direct detection limits, these shapes tell us something about the dark matter that's coming in, and also a little bit about our astrophysics. So in the low mass region, dark matter does not have enough kinetic energy. It's too low mass to actually form a sizable nuclear recoil. So these experiments are not very sensitive to those, and thus we had to move to electron targets and towards the low masses. Now, once we get to the higher masses, we get more and more sensitive because it's like hitting a billiard ball with a billiard ball. So I have proper sizable nuclear recoils. Now, once I start going to higher and higher masses, the kinematics don't matter as much, and now my astrophysics starts kicking in. And so the number density that goes is the density in our local ambient region over the mass of the dark matter. As I increase the mass, the dark matter number density decreases. If I just crank this number high enough, these experiments become less and less sensitive to a point where I can get to very large cross sections. These large cross sections means that now dark matter can be strongly interacting with the standard model. And so instead of actually getting into the dark matter coming into the detector and interacting only once, it could actually interact multiple times inside my detector. So the heavier the mass, the larger the probability of interacting multiple times. So, depending on some nuances and theories, of course. And in principle, actually, current experiments could search for this. We don't need to build bigger, newer, bigger detectors. So xenon 1 ton or near future detectors could actually look for this. So currently they're searching for one dark matter particle coming in and giving on some scintillation signal. In principle, one could have a particle, even though there are few of them in our local region, those small number of particles could come in, hit the detector multiple times and cause multi-scintillation signal. And in principle, this signal would be very different from any other background that we have. The only background that could mimic this is neutron backgrounds. But again, a neutron is around 1 GeV, and every time it interacts, it gives a momentum transfer of 1 MeV. So you'd see for neutron, you'd see a kind of a disappearing multi-scattering signal. Whereas if I have a 10 to the 16 GeV particle that is interacting multiple times, and every time it interacts, it only gives off, say, 1 MeV momentum transfer, then I basically have a strong signal of just this particle just boom, 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 boom in my detector and giving off a strong constant signal. And so this is a striking signal for these kind of particles that we should actually be looking for in our detectors. So multi-scattering signature was first discussed in this paper, in these two papers by Joe Bramante, Benjamin Bluman, Raphael Langen from PMR. And then the other ones then included Jason Kumar and Maxime Pospelov. Here, Dharma actually in the late or early 90s searched for this signal through timing, and they put a limit on the mass versus cross section. Here, these are projections for the xenon 1 ton multi-scattering and the Darwin multi-scattering with a 10-year flux limit. This is just an extrapolated limit from the xenon 1 ton experiment, and this here is an extrapolated projection for the Darwin with just one scattering in the detector. And so if we look at this, these correspond to cross sections of roughly 10 to the minus 33 square centimeters. The flatness of these lines just corresponds to the flux of the and the optical depth that you expect from these huge, these large mass particles. And so Human and I sat down and asked what kind of physics can give us these kind of cross sections? Well, the simplest thing to think about is that if I look at the direct detection cross section, it goes as 1 over the mass of the mediator to the power 4. And so the smaller the mediator, the larger the cross section I can get. Well, what kind of theory could I get where I'm linking coupling a very small mediator to a 10 to the 16 GeV mass without actually affecting the mass of that mediator through radiative corrections? Well, we know that vector bosons are protected by gauge symmetry. Their masses are protected by gauge symmetries. So let's just consider some gauge symmetries. Well, I can consider as many gauge symmetries as I want. How can I get actually some symmetry that's going to be actually go down to the lower scales and survive so that I can get this low mass mediator? It turns out that the simplest gauge group that we all in most of our theories consider, which is just the U1, enjoys this property. So if it's embedded in a very large high scale theory, that gets broken down up until the lower scales. The U1 usually survives and then gets explicitly broken down. And this was realized in this paper by Jim Halverson and Paul Langecker in 2018. So using this, exploiting this possibility, we proposed a dark gauge group. So they called that U1 dark that has a vector boson A dark. So for the explicit example, we assume that this is gauge barrier number that has this following Lagrangian of interactions. So this is the dark charge of the quarks, which is just the normal baryon charge of a third. This is the dark charge of the baryon charge of the dark matter. And because of loop induced processes, we have a kinetic mixing with the standard model of leptons and fermions. So the direct detection of this ultra heavy dark matter through a light messenger goes through this process, this T-channel process here, where I have the direct detection cross section again goes as those charges, the gauge coupling squared over the mass of the mediator. And then there's this reduced mass piece over here, which actually calculated for very large masses just reduces to the nucleon mass. And so for cross sections of 10 to the 33, we realize this 10 to the minus 33 square centimeters. We realize that this is actually independent of the mass of the dark matter. And so then I can plot this as a function of the mass. So from the gauge coupling squared as a function of the mass of the mediator. And for this, then I plot the alpha dark as a function of MA dark and show the limits for a baryonic mediator on rare meson decays. These are from GlueX and other rare meson decay experiments. This line here searches for epsilon 1s decays to hadrons. And these lines are, if I remember clearly, these lines were the solid, like older constraints, and these were projections. But possibly with the recent UX data, these could have been. In any case, these lines, these dotted or dashed lines here, are the spin-independent cross sections that we expect from this model. And so I draw a crude line here to show that for Xenon 1 ton and Darwin with those flux limits that I showed before, above here I could get multi-scattering signature. Below here I could get single scatter signal. And so this tells us a few things. So that because of the independence of the mass of the dark matter here, I could actually, in principle, there's some complementarity between the direct detection searches for ultra heavy dark matter and also the low energy searches for the mediator. So if we go and we search for ultra heavy dark matter and see this multi-scattering signal, that tells us, this model actually tells us to go and look in this parameter space for this baryonic gauge vector particle. Now, I've told you about this interesting signal in direct detection experiments, but I actually haven't told you how we could produce this type of dark matter particle. So there are many ways that we could produce dark matter in the early universe. We heard about one interesting way this morning, 2 talks ago. So there's freezing, there's asymmetric dark matter, but a very well motivated way is also thermal freeze-on. And in fact, like this is the way that WIMPs produced in the first place. Now, the thermal equilibrium with the standard model path requires large couplings in order to be in thermal equilibrium and in order to give us the required abundance. But also, those large couplings help us detect dark matter after the universe is expanded in present time. Now, we know the one main problem with thermal freeze-on, right? The one main wall with this is that if I want my dark matter to be elementary, if it's heavier than 100 TeV, then I'm overproducing dark matter, which is not what we see. This is called this is what we know as the unitarity limit, that is at 10 to the 5 GeV. So how do we get around this unitarity constraint? Well, there are many creative ways of doing this and that people have come up with. For example, and I will not go through all of these in detail, and these are very interesting papers that I invite people to look at. So there's super heavy dark matter from thermal inflation, where dark matter is produced immediately after inflation, after the inflaton rolls in its potential and sources a large mass for the dark matter. Now this model is somewhat similar, but has different assumptions to what I'm going to be talking about later. There's thermal dark matter from a highly decoupled sector, where the dark sector and the standard model sector have 2 different temperatures, kind of similar to what Nicolás was talking about earlier. And the dark sector, the dark matter annihilates into secluded sector, so annihilates into dark photons that then are weakly coupled to the standard model sector. As the universe expands, the entropy is dumped into the standard model sector and is diluted away by the expansion of the universe. And this is how you set the relic abundance of these super heavy particles. And there's also thermal dark matter from primordial asymmetries, which is kind of similar to this, but you're dumping entropy again into the standard model sector, but then you're looking now at asymmetric dark matter that is formed from baryogenesis or like some baryon asymmetry that was formed before. And again, the entropy dumping into the standard model sector sets the relic abundance of these asymmetric particles. And again, if James is in the audience, if I said something wrong, please correct me. There's another interesting idea here from filter called filter dark matter, whereby one forms in the early universe. There's a there's a I'm forgetting my words now. But in the early universe, there's a phase transition after symmetry breaking, and bubble nucleation occurs. And so we have two phases. Inside the bubble is a VEV, non-zero VEV that is very large. Outside the bubble, the VEV is zero. So dark matter goes from outside the bubble and tries to get filtered inside the bubble. If it has a large enough momentum, it filters through. If it does not, it does not get into the bubble. So a very small number of dark matter particles get into this bubble. And once the bubbles merge and we have the universe that we have today, the large wave gives the dark matter, the small number of dark matter particles, very large mass. But then they give this very large mass, and this sets the Rayleigh abundance of these dark matter particles as we see them today. So these are all very interesting ideas that of how to get around this unitarity limit for thermal super heavy dark matter. And there are many other theoretical possibilities here, and again, I invite you to take a look at these papers. So today I'm going to be telling you about thumps. This is a work that I did with Mark. So thumps stands for thermal ultramassive particles, and I have to admit that these logos don't necessarily look thumpy; they look more like a crunch. But the idea of thumps, rather than more than a play of words on this acronym, was more like the idea of a very heavy object that lands on another object, gives you kind of a thump noise. The main idea here is that dark matter is light. It's ultralight before freeze out. It's basically a WIMP. Well, not ultralight. It's just a WIMP before freeze out. And before freeze out, we require to annihilate very efficiently, such that after freeze out, you have a very small number density of these particles. The dark matter then is coupled to an ultralight scalar that, when it grows in its potential after freeze out, gives this dark matter sources a huge mass for the dark matter. So you have an initial mass, and after freeze out, you have a final dark matter mass. So one concrete example we considered here was a dark matter coupled to a dark photon that has this kinetic mixing. This potential for this ultralight scalar is just a simple potential, and there's this Yukawa type interaction that gives the dark matter its final mass. And so before freeze out, we assume that the dark matter, initial dark matter, is larger than the mediator mass. And then in that case, the dominant annihilation process is just a secluded annihilation into these dark photons that then decay into fermions. And so if we crank this gauge coupling up, this annihilation process is very efficient, such that this number density, this annihilation cross-section is very large. And so after freeze out, immediately after freeze out, this ultralight scalar starts rolling in its potential, reaches its minimum, and sources this large mass for the dark matter. Now, the benchmark parameters that we chose for this is that lambda is 10 to the minus 6, the M phi is 10 to the minus 14 EV, and phi is 10 to the 15 GeV. Now, I can already feel you cringing that these numbers are very huge, right? And we can discuss this a little bit later. But again, this is a phenomenological model. There is a big hierarchy between the mass of the phi and this potential. Right? However, if one is comfortable with some fine tuning, or there is one could come up with a UV completion where this fine tuning will go away, then this is a possible viable theoretical, a viable phenomenological possibility. So the Rayleigh density then here is given by the number density, which depends on the initial dark matter mass, and times this final dark matter mass here. And so here I plot a function, the final mass as a function of the initial mass, and plot the Rayleigh abundance, the correct Rayleigh abundance line, as a function of these two gauge couplings. So here we see that for at the limit of the gauge coupling, so here G dark is about 4 pi. At that limit, the highest I can reach is about 10 to the 9 GeV before I get into BBM. and I will explain what the speaker about.
Gopi, you have around 5 minutes, okay?
Okay. And so in this case, then here we've got the initial dark matter mass as a function of the freeze out parameter. And again, we see that in order for me to get the largest masses, meaning that I have to start at the lowest dark matter mass possible before reaching the BBN bound, I need to freeze out much later. So I'm actually freezing out at this point right at the edge before BBN. Now I cannot freeze out in this case in here because once dark matter annihilates in this region into into dark photons that then decay into the standard model, that disrupts the elemental abundances, which, as we know, is not allowed. And so in this case, then I can go and look at the direct detection of this kind of dark matter. Again, we go back to the spin-independent cross-section that I had before. This, again, is independent of the final dark matter mass, the heavy guy, which is now available in our local region. And so in this case, then I can plot like the normal kind of beam dump dark photon bounds, but then I can overlay the direct detection cross sections on top of that. And so this gives me here for benchmark parameters where I have an alpha dark of 1, MChi of like an MChi final of 10 to the 7 GeV. How I got to this 10 to the 7 GeV is we assume here that we're dealing with a roughly 1 GeV photon particle, taking this constraint here that we set, that the initial mass would be twice the dark photon. Then I'm looking roughly at, say, 2 GeV. This gives me, say, something like 10 to the, actually it should be here. So that's something at roughly 10 to the 5. 5 times 10 to the 7 GeV, sorry. And so with this benchmark parameter here, I can then extrapolate the xenon 1 bounds. Because of all these limits from the epsilon, we realized that we can't actually get the multi-scattering signal that we got in the previous model. And so this is a single scattering, and therefore then we have to look at the xenon 1 bounds, extrapolated bounds. So this whole red region here is excluded by xenon 1, and this gray region is excluded by the normal beam dump searches that we know. And so this leaves us with this small region of parameter space, whereby the dark photon can be searched for at sequence, at darkwest, at chip, and the dark matter can be searched for at Darwin. However, if we find a way to search for this kind of dark matter in the neutrino floor, then we have this region of parameter space that we can go and look for as well. So again, we see this kind of complementarity between the low energy experiments that search for mediators, for this type of mediator, and the direct detection experiments that search for this super heavy dark matter. And so the takeaway that we have here is that since we don't know what dark matter is, so there are many avenues that we need to look at. And I would say we really need to look at as many avenues as possible. And so discussions like these, where we have many great ideas, where we can talk about the dark matters, I think it's a wonderful thing when we learn from that. Here I discussed 2 possible models for detecting this kind of dark matter. One where we have a possible multi-scattering signal in direct detection experiments, and one of how to produce these particles in the early years. And again, this gives us some possible complementarity between the super heavy, ultra heavy dark matter searches and low energy experiments. And with that, I say thank you.
Thank you, Gopi. We're running very late, so if there is any urgent question before the break, of course there will be discussion sessions afterwards. So, any questions then for Gopi? Don't see any hands. So if not, thank you again, Gopi, for your talk. I have some questions, but I think I will postpone for the discussions. So let's have a break now, and we're running a bit late, but let's try to resume in 10 minutes, okay? At 11:45, so that we keep with the program. Thank you very much. See you in 10 minutes.